There is a number that has quietly haunted the field of astronomy for years. Not a theory, not a hypothesis, a number. It comes from a study published in 2020 by a team of researchers using data from the Atacama Large Millimeter Array in Chile, combined with deep field observations from the Hubble Space Telescope. The number is this. The universe appears to contain 10 times more galaxies than we previously thought. Not 10% more, 10 times more. That means our estimate of 200 billion galaxies was off by a factor of 10. The real figure, based on that study, is closer to 2 trillion. 2 trillion galaxies, each one containing hundreds of billions of stars, each star potentially orbited by worlds. And we had been wrong about the count by an order of magnitude for decades. That study made headlines for about a week. Then the news cycle moved on. But the scientists did not move on, because hiding inside that number was something that nobody had a clean answer for. If there are 2 trillion galaxies out there, and the universe has been running for nearly 14 billion years, and the conditions for life as we understand it are not rare but abundant, then where is everybody? That question has a name, the Fermi paradox. And in the years since that galaxy count was revised upward, the James Webb Space Telescope has been quietly making it worse. Let's go back to the beginning. Not the beginning of this story, the actual beginning. Approximately 13.8 billion years ago, the universe erupted into existence. In the first few minutes, the lightest elements formed: hydrogen, helium, trace amounts of lithium. For the next several hundred million years, the universe was dark. No stars, no light, just an expanding ocean of gas slowly cooling and beginning to clump under its own gravity. Then the first stars ignited. They were enormous, hundreds of times more massive than our sun. They burned fast and died violently, seeding the surrounding gas clouds with heavier elements forged in their cores: carbon, oxygen, iron, the raw ingredients for rocky planets, for chemistry, for the kind of complexity that, given enough time and the right conditions, can begin to organize itself into something that asks questions about the universe it lives in. The standard model of cosmology tells us that this process took time, that the early universe was a chaotic place, hostile to the gradual, patient assembly that complex structures require. Galaxy formation was supposed to be slow. Star formation was supposed to be slow. The development of stable planetary systems was supposed to require generations of stellar evolution, each cycle enriching the surrounding medium with more of the elements that make planets like ours possible. That is what the models predicted. That is what every major cosmological simulation confirmed. That is what the scientific consensus held, with high confidence right up until James Webb turned on. Within months of beginning observations, Webb began finding galaxies that had no business existing when and where they did. Fully formed, massive, structured galaxies seen as they appeared just 500 million years after the Big Bang, some of them rivaling the Milky Way in stellar mass. Galaxies that our model said should have taken billions of years to assemble had apparently done it in under a billion. The reaction from astronomers was not dismissal, it was something closer to controlled alarm. But here is where the story takes a turn that most science coverage missed entirely. The galaxy formation problem, as striking as it is not the strange thing James Webb found. It is the context for the strange thing James Webb found. And understanding the context is what makes the strange thing so difficult to look away from. To understand what Webb actually detected, you need to understand something called the cosmic biosignature problem. And to understand that, we need to talk about a molecule called dimethyl sulfide. Dimethyl sulfide is a sulfur-containing organic compound. On Earth, it is produced almost exclusively by marine phytoplankton, microscopic organisms in the ocean. When phytoplankton metabolize certain compounds, they release dimethyl sulfide into the atmosphere. It contributes to the characteristic smell of the sea. It plays a role in cloud formation. It is, as far as we have ever been able to determine, a product of biological activity, not geological activity, not stellar chemistry, biology. In April 2023, the James Webb Space Telescope observed a planet called K2-18b, located approximately 120 light-years from Earth in the constellation Leo. K2-18b orbits in the habitable zone of its star. It is classified as a Hycean world, a theoretical category of planet with a hydrogen-rich atmosphere and a potential global ocean beneath it. Webb's instruments analyzed the light that passed through K2-18b's atmosphere as the planet transited its star. The technique is called transmission spectroscopy. When starlight filters through a planet's atmosphere, Different molecules absorb different wavelengths. The pattern of absorption acts like a fingerprint, allowing scientists to identify which molecules are present without ever visiting the planet. Webb found carbon dioxide. It found methane. It found carbon disulfide. And it found a potential signal that the research team, led by Niku Madhusudan at Cambridge University, identified as possibly consistent with dimethyl sulfide. The word possibly carried enormous weight. The signal was at the 2.5 sigma level, which in scientific terms means suggestive but not confirmed. The threshold for a definitive detection in physics is typically 5 sigma. 2.5 sigma means there is approximately a 1 in 80 chance the signal is noise. Those are not the odds you build a press release around, but they are also not odds you dismiss, especially when the molecule in question has no known non-biological source, and the planet in question is sitting in its star's habitable zone, with an ocean potentially beneath it. Madhusudan was careful. He said the signal was tentative. He emphasized that further observations were needed. He used every hedge available to a scientist who does not want to be wrong in public about something this consequential, but he also said something that was easy to miss in the careful language of the official paper. He said that if the signal were confirmed, it would be difficult to explain without invoking biological processes. Difficult to explain without invoking biological processes. Read that again. A Nobel Prize-winning physicist did not make that statement. Madhusudan did not win a Nobel Prize. But here is what a Nobel Prize winner did say, and this is where the title of this video connects to the science underneath it. Frank Wilczek is a theoretical physicist at MIT. He won the Nobel Prize in Physics in 2004 for his work on the strong nuclear force, one of the 4 fundamental forces of the universe. He is not an astrobiologist. He is not someone who studies planetary atmospheres. But in the years since the James Webb detections began accumulating, Wilczek has spoken publicly about what the emerging picture means. He has argued that the conditions for life in the universe are not as rare as the models once suggested, that the revised galaxy counts, the early universe findings, and the atmospheric detections all point in the same direction, that the default assumption in cosmology, the assumption that we are probably alone, is becoming increasingly difficult to defend not on philosophical grounds, but on purely statistical ones. He put it this way: the universe is not structured like a place that produced life once by accident. It is structured like a place that produces life wherever the conditions permit. And the conditions, it turns out, permit more than we thought. That is not a mystical claim. That is a reading of the data. Let us look at the data more carefully. The Kepler Space Telescope, before it was retired, surveyed a small patch of sky containing approximately 500,000 stars. From that survey, astronomers estimated that roughly 1 in 5 sun-like stars hosts an Earth-sized planet in the habitable zone. 1 in 5. Scale that to the 2 trillion galaxies Webb has helped us count, multiply by the average number of sun-like stars per galaxy, and the resulting number of potentially habitable worlds is not millions or billions. It is a number with more zeros than most people are comfortable thinking about. The TRAPPIST-1 system, discovered in 2017 and subsequently studied in detail by Webb, contains 7 rocky planets orbiting a red dwarf star about 40 light-years away. 3 of those planets sit in the habitable zone, 3 of them. In a single star system, 40 light-years from Earth, there are 3 worlds where liquid water could exist on the surface. Webb has analyzed the atmospheres of several TRAPPIST-1 planets and found, in one case, tentative evidence consistent with a secondary atmosphere, the kind that forms when a planet is geologically active and potentially capable of sustaining complex surface chemistry. Red dwarf stars like TRAPPIST-1's host star are the most common type of star in the universe. They make up approximately 75% of all stars. They burn slowly and steadily for trillions of years, far longer than our sun will live. If life can take hold around red dwarfs, then the window for life in the universe is not billions of years long. It is trillions of years long. The universe could be, in a very real sense, only just getting started. But the Fermi paradox still hangs over all of this like an unanswered question carved into stone. If life is so plausible, if the conditions are so widespread, if the universe has been running for nearly 14 billion years, then the silence is not just surprising. It is deafening. We have been scanning the sky for radio signals since 1960. 60 years of SETI research. We have detected nothing definitive, not one unambiguous signal, not one artifact, not one structure, just silence. There are many proposed explanations for this silence. Some are comforting, some are not. One explanation is the Great Filter. The idea, developed by economist Robin Hanson in 1998, is that somewhere between the formation of a star and the development of a civilization capable of making itself known across interstellar distances, there is a step so improbable, so catastrophically difficult that almost nothing gets through it. The Great Filter. The question that keeps serious thinkers up at night is whether that filter is behind us or ahead of us. If the filter is behind us, then we got lucky. Life on Earth navigated some improbable gauntlet, perhaps the emergence of the eukaryotic cell, perhaps the development of sexual reproduction, perhaps the specific conditions that allowed complex multicellular life to arise. We are the exception. The cosmos is mostly dead, and our existence is a fluke so improbable that it may never have been replicated elsewhere. The silence makes sense because almost everything fails before it gets interesting. If the filter is ahead of us, then the silence is a warning. It means civilizations like ours regularly reach a certain threshold of technological capability and then disappear. Every civilization that has ever developed interstellar communication has gone quiet. The silence is not the quiet of an empty universe. It is the quiet of a universe full of ruins. The James Webb findings cut directly into this debate in a way that previous data could not. If Webb's early galaxy observations are correct, if massive structured galaxies existed within the first billion years of the universe's history, then the timeline for life to have arisen elsewhere is far longer than the models previously allowed. A civilization that arose in one of those early galaxies would have had 12 or 13 billion years to develop, to expand, to leave marks, to be detectable. And we detect nothing from them. That absence is data, not proof of anything, but data. Avi Loeb, the chair of Harvard's astronomy department and one of the most publicly visible scientists working on the question of extraterrestrial intelligence, has argued this point with a directness that his colleagues sometimes find uncomfortable. Loeb does not deal in comforting hedges. He has said repeatedly and on the record